So we start with something called a conditional statement. Now I'm going to be really generic, and I'm just going to use my P's and Q's, and we can fill in the blanks of what P and Q mean, for example. So if I said P and Q are going to be statements, quite simply. If P, then Q. Let's keep it really simple. P will be, we scored more points. Q will be, we win the game. So if we score more points, then we win the game. That would be a perfect example. P, again, is a statement. P might be 4x equals 8. Q might be x equals 2. So if 4x equals 8, then x equals 2. That would be a conditional statement. A conditional statement, P is called the hypothesis, Q is called the conclusion. If P, then Q. And we usually write it, if I'm making statements, we usually use the double bar if it's a mathematical statement. What's a little bit confusing is when we're doing logic, we use different symbols. For example, you know, the intersection and the union symbols, you know, the upside down U and the right side up U. But in logical statements, we use the sort of the triangular of the same, right? The same things, but we use that sort of a triangular version. So what we do in this case, in the logic, and I'm not a big fan of this, we actually use a single arrow in the logic to mean the same as the implication symbol does the rest of the time. So if you were taking calculus, oh my gosh, this can be mind-numbingly confusing. We know this is the implication symbol. P implies Q. This would be the symbol we use for approaches in a limit. And we use both of them during the course. So these have very different meanings in a calculus context because one of them we use for the limit. In this context, we use this symbol is the same as this symbol in this context. And we will actually use the implication symbol later on when we're doing certain things. I'm not a fan of using it in this context, but that's what it is. P implies Q means if P, then Q. If P is true, then Q is true. And you could go forever and ever and ever, okay? That's called a conditional statement. The converse is if Q, then P. Now, the converse is a statement. The question is the converse true? Not necessarily. If a shape is a square, then it is a rectangle. I think we all agree that's a true statement. If a shape is a rectangle, then it is a square. Could you draw a rectangle that's not a square? I think you could. So the converse would not be true. In fact, in general, most things, the converse isn't true at all. But the problem is the converse sounds just like the conditional. So there's a tendency to automatically assume it's true. So if this thing happens, then this thing is going to happen. And the other thing happens, that means this thing's going to happen. And sometimes we switch them unknowingly. We're going to do several examples of that today. Okay. So if both are true, okay, if both of these are true, then we have what's called a biconditional. And we say that, in this case, by the way, I'll use the notation again. This is P implies Q. This is Q implies P. Biconditional, we say P, and we have the arrow going both ways. P implies Q and Q implies P at the same time. Does anybody, what's the mathy expression that we use? Does anybody know? I'm sure you've all heard it. What's the mathy? That's a word. The mathy term that we use when we do a biconditional. Anybody know? I think you've all heard it. We say if and only if. And then the universal math way of saying that is we actually write IFF, which makes me laugh because, you know, that's not actually a word, IFF. IFF is sort of the universal math slang for if and only if. Now, the statement if and only if means A implies B and B implies A at the same time. So A is true if and only if B is true and vice versa, okay? Biconditional is when A implies, or excuse me, P implies Q and Q implies P. So either they're both true or neither one of them are true. Okay, it's a all in one. So we often say if and only if. So P if and only if Q. So if we win the game, it's because we scored more points. If we score more points, we will win the game. So we will win the game if and only if we score more points. That would be an example of a biconditional. Now, what about the negations? Where do they fit into this? Well, then we have something called the inverse. The inverse would be not P implies not Q. And the contrapositive is not Q implies not P. Now these are where it gets a really tricky. This is why I said sometimes we make false conclusions because it sounds good. If the conditional statement is a true statement, in other words, you're not being lied to. Think of a conditional statement like a promise. You know, if you hold up your end, I'll hold up my end. If the hypothesis is satisfied, the conclusion is guaranteed. That's what a conditional statement says. So assuming that statement is true, only one of these is automatically true. The converse, the inverse, and the contrapositive, only one of them is automatically true. If we score more points, absolutely guaranteed we will win the game. We didn't win the game today. Can anybody make a conclusion? Blurt it out. We didn't win the game today.
Then we didn't score more points.
Then we didn't score more points. That's the contrapositive. The contrapositive and the conditional say exactly the same thing. Wait, no, they don't. This one's all negatives. Yes. If the occurrence of P guarantees that Q is going to happen and Q didn't happen, then P couldn't have happened. That's what it means to be the contrapositive. And we use this all the time. I gave this analogy last day. This is exactly how the legal system has always worked. And by the way, that goes back to the ancient Greeks. If all this stuff is true, you know, we're going to show you're guilty. We're going to show all this stuff leads to guilt. So what do we start? Assuming not guilt and show that it leads to not all of this stuff. You know, and when I come up with a contradiction, then my assumption of not guilt was an incorrect assumption. But if I can show not guilt, hey, you were never associated with anything at the other end. Okay, so this is called a proof by contradiction because we're actually using the contrapositive of a conditional statement. That's actually how it's always worked. Yeah, it seems kind of backwards, but if you've ever done a geometry proof the same way, I'm trying to show that this information leads to this conclusion. So I start by assuming not that conclusion and then show it goes the other way. Again, this sort of logic. So if I can show that not Q leads to the conclusion of not P, then I can absolutely say that P implies Q, that they work hand in hand. So by the same token, the inverse and the converse work hand in hand. Okay. Now we don't say the contrapositive is the negation. That's not true. No, the negation of a statement is something else. We'll get to that. So identifying statements is actually pretty simple. So if I gave you two statements, we call them P and Q, then if I said, well, give me all of these. Okay. So if I said, I'm going to give you a statement and it could be anything, you know, Biff is enrolled in math could be one of the statements. And the second statement is, you know, Muffy likes cake. I don't know. So now if Biff is enrolled in math, then Muffy likes cake could be my conditional. If Muffy doesn't like cake, then Biff isn't enrolled in math would be my contrapositive. You can go all day. What I used to do when I taught high school geometry is I actually would use, there was two things I would use. One of them, I'd use the Jabberwock. Everybody know what the Jabberwock is? 'Twas brillig and the slithy toad, did gyre and gimble in the way of all mimsy where the boar grows and the gnome wraths outglade. Alice in Wonderland. It's a gibberish poem that when you read it, you get this mental image, but if you actually read the poem, there are no real words in the poem. So I would use gibberish. If a lemshin is, you know, and I just start making up words, but I'd have an if and a then in there. And then I'd ask them, give me the converse, the contrapositive, of gibberish statements. And they could actually do it perfectly because they didn't try to think what that gibberish statement meant. Then when we do a real geometric statement, you know, if a polynomial has, or a polygon, excuse me, has this many sides, then, you know, it was much easier for them to do real statements if they started with the silly stuff. And it actually worked very, very well. Of course, they had to relearn how to speak English later on, you know, because I'm making up all these words. So we could do this kind of stuff all day. Now, so the next ones I want to introduce are what we call necessary and sufficient. And people often get these ones confused as well. Now, when we're talking about mathematical statements and mathematical proofs, necessary and sufficient are also considered weak and strong statements. When we talk about things like qualifiers, okay, everybody here hopefully is familiar with the universal qualifier and the existential qualifier. Existential, I can't spell it very well. This is called the universal qualifier. This is called the existential qualifier. The universal qualifier literally means for all or for every. The existential is there exists. And what's the difference? There exists means there is at least one occurrence, but there might only be one occurrence. For all means every possible occurrence. So for all could literally be infinite. Okay, so there, one is called, that's called weak, that's called strong. Necessary and sufficient, one is weak, one is strong. So when, I'll use Calc 2 as an example because everyone here's had Calc 2. You were doing sequences and series, and you were trying to determine if a series converges or diverges. You guys remember how much fun you had doing that kind of stuff? Oh boy, yeah. So turns out we had something called an nth term test. If the terms are getting smaller and approaching zero, then we got on our horse and we tried to prove whether that thing converged or diverged. Because if I could show either one of those things failed, if my terms were not getting smaller or my terms were not approaching zero, then my series diverged. It was a piece of cake. So proving the nth term test, or that it satisfied the nth term test, did not prove that it converged. It was failing the nth term test proved that it diverged. So passing the nth term test was called a necessary condition for convergence. But it didn't mean convergence. It meant failing it guaranteed that you didn't. So I like to use the following example. All right, we're going to play in a contest today. I would say football, but football is now done. Okay, so maybe we're going to play in a hockey game. All right, we're all going to play in a hockey game tonight. A necessary condition for us to win the game tonight is that we actually show up. Now, showing up doesn't mean we're going to win the game, but not showing up guarantees we're going to lose. You see, a necessary condition if you get an A in this class is that you're actually enrolled in this class. See, if you're not enrolled in this class, you can't get an A because you won't get a grade. So a necessary condition does not guarantee the conclusion. Failing to satisfy the necessary condition guarantees the conclusion will not happen. Does that make sense? So necessary is weak. So a necessary condition for success in this course is that you're actually enrolled in this course. That's okay. Now, necessary, if you fail a necessary, okay, then you're not going to have your conclusion. Now, a sufficient condition. All right. A sufficient condition for an A in this course is that your average is over 90%. That's a sufficient condition. So if that happens, you're guaranteed success in the course. All right. So a sufficient condition for us to win the game tonight is that we outscore the other team. A necessary condition is that we actually showed up, but that won't give us victory. But if we outscore the other team, then we're guaranteed to win. Okay. So a sufficient condition, that would be a strong mathematical statement. Okay. So I always like to use things like this. You know, a necessary condition for happiness is that you have wings at least once a week. That's necessary. Now, having wings once a week, does that mean you're going to be happy? Not necessarily, but not having wings at least once a week means you're not going to be happy. Okay. But a sufficient condition for happiness might be that you have an ample supply of IPA in the fridge, which I do, by the way. So a sufficient condition for happiness is having an ample supply of IPA. If I'm happy, then clearly that's good enough. But if I don't, then I won't. So these are still conditional statements in the, P implies Q, but you have to look at the other way. So now let's think of it this way. If a necessary condition for us to win the game tonight is that we actually show up, okay? Is that we actually show, that's necessary for us to win the game, that we show up. We won the game tonight. Can you conclude that we showed up? Yes, you can. You see, if a necessary condition for winning the game is that we show up, if we don't show up, then we definitely lost the game. So if we won the game, we had to have shown up. Okay? Does that make sense? So you can also look at it from the opposite point of view. And again, you're going to be writing and messing around with statements. So if a sufficient condition for us to win tonight is that we outscore the other team, then if we outscore the other team, we're definitely going to win. We didn't win tonight. And we didn't outscore the other team. So I'm doing it from the negative standpoint as well. Okay. Now, the last one of these that I want to go over. Lost my eraser for a second. The last one, and probably the trickiest one a lot of times, is the negation of a statement. Okay? The negation of P implies Q. All right? The negation of something, okay, means that you can have the opposite conclusion of what it is. Remember this binary, Q either happens or it doesn't happen. So if we score more points, then we will win the game. We scored more points. Finish this for me. I want the negation. We scored more points, but we didn't win the game. Wait a minute. But if you score more points, then you win the game. But the negation of that is we scored more points, but we didn't win. Remember, but and work the same in logic. So the negation would be P and not Q. We scored more points and we didn't win. So the negation of P implies Q is P and not Q, which, by the way, is not intuitive right off the bat until you start thinking of all the different scenarios. But I'm going to show you a different way. We're going to do it as a truth table. Okay? So I want to show that these are equivalent. And this is always the most powerful because it's easy to get things confused. It's easy to put the negation in the wrong place, to switch the ands and the ors and so on. So let's make a truth table. We have P, we have Q, we have not Q, we have P implies Q, we have P and not Q. So there's 5 categories here, and it's the last 2 that I want to compare. Okay? Use the orange here. So P is true, Q is true, P is true, Q is false. P is false, Q is true, P is false, Q is false. So now the negation of Q, I just do the opposite of what I have in each of those positions. Now, P implies Q. This is a little bit tricky. I want this one to be an absolute slam dunk for everybody in here on a regular basis. There are 4 possibilities. The only time, think of it, I like to think of it, if a conditional statement is like a promise. If the hypothesis occurs, the conclusion is guaranteed. You've all had situations in your life where you feel like somebody lied to you because the hypothesis occurred, but the conclusion didn't happen and you were guaranteed that's to happen. Okay? Which of these is a lie, in other words? Only one of these is actually a lie. Now that's, you're like, wait a minute, only one of them's a lie? Yeah. Now think of it another way. If we score more points, then we win the game. The lie would be, obviously, we scored more points, but we still didn't win the game. That would be the one you'd say, I'm suspicious. But what if we don't score more points? Well, I never met the hypothesis. There can't be a lie if the hypothesis wasn't. Oh, we didn't score more points, but the other team didn't show up, so we won on a forfeit. Yay. We didn't score more points. The other team won the game, but hey, we didn't score more points. The hypothesis didn't occur. It can't be a lie. So both of these make this true because I didn't lie to you. You didn't satisfy the hypothesis. So the conclusion is up in the air. Oh, so you scored more points, you won the game. Great. You scored more points, but you didn't win. Somebody lied to us. That's the only time a conditional statement is false. The other two are still true because, again, if the hypothesis hasn't been met, it doesn't matter about the conclusion. That again, defies logic at first sometimes. Now, the last one is P and not Q. So they both have to be true. P and not true, excuse me, P and not Q. Did I say that correctly? P and not Q. Okay. Okay, so P, where's P and not Q? So look at this. And I think that's it. Okay. So true, and then the other ones are false. P implies Q. P and not Q. I got exactly the opposite, don't I? So every single one of, that's why we call it the negation. Every single thing was just the opposite. So P implies Q, P and not Q. Now, going back to, this is the one that everybody always has trouble with at first, because it seems like, for most people, it seems like that's the only time this is true. Okay. So the negation of something, okay, the negation is not the contrapositive. Okay. Remember the contrapositive, if we score more points, then we win the game. We didn't win the game, therefore we scored more points. Those are identical statements. We scored more points, yet we still didn't win the game. Wait a minute, right? You know, so if you look at it that way, you go, wait, that seems like it failed. Well, that's where it's the negation. So the negation, the converse, the contrapositive, all of these things basically are just simple definitions. So if you're given a logical statement, you just, how do I say those things? That's it. That's all I want you to see. Now I'm going to move on to the next thing, because we want to talk about valid and invalid arguments and the nature of things. And this is where I have fun. I was actually meeting with a student before class today. We met on Zoom, and he was asking me about discrete math. He's a calc student. And I said, well, we discussed logic. He says, well, what's the point of discussing logic? I said, a lot of times you read something mathematically and you're saying, okay, I'm reading the words as is. Are there other ways I can interpret that statement and have it still be true? Now, remember what we did last day. We looked at things, you know, P and Q or not, you know, we looked at, sometimes there were tautologies, sometimes there were contradictions, meaning sometimes didn't matter what statements I put in there, that thing was always true, period. Because of the way we combined a whole bunch of stuff, there were other statements that were always false. So sometimes I can have something fairly complicated, but I can whittle it down to a really simple statement and say, oh, okay, I can also say this is true if my original thing is true. I got all these little pieces. So we call them valid versus invalid arguments. And a lot of times, and I'll give you a simple example, right? Every square is a rectangle, but sometimes we hear every rectangle is a square. I used the same words, but we got them backwards. And that's the converse. And that would not be a correct statement. So my favorite one to start off, I always use this one every semester. I always do this when we're in the classroom. All cheaters sit in the back row. Larry is sitting in the back row. Therefore, Larry's a cheater. You're all going, yep, yep, yep. Larry's nailed. Is that a correct conclusion? Did I make a correct conclusion there? All cheaters sit in the back row. Larry sits in the back row. Therefore, Larry's a cheater. Actually, it's not true. And it's called the converse error. If P implies Q, I just said Q implies P. All cheaters sit in the back row, but the back row isn't exclusive to cheaters. There might be non-cheaters sitting in the back row too, but if you're a cheater, you're definitely sitting in the back row. But the back row is really big, right? All sorts of people. Heck, farm animals are in the back row. Who cares? Larry just happens to be in the back row. Now, all cheaters sit in the back row. Larry, he's a cheater. Can you make a conclusion? Yes, Larry sits in the back row. That would be a valid conclusion. Now, you see my point? Poor Larry. I don't know if your name's Larry, I'm sorry. I usually use Larry because I never have Larrys in the classes, but then again, I don't usually have Biffs either. So that's the kind of stuff that people make mistakes on every single day of your life because it sounded correct. Well, one version was correct, one version was not. And so, in other words, I have a conditional statement, but I could also have the converse. And then we also have other types of errors, okay? One of my favorite ones to use on a test, I'll usually say things like, all Lannisters pay their debts. Tyrion is a Lannister. Therefore, can you say Tyrion pays his debts? Is that a correct conclusion, or did I just make the converse error again? This is where you got to think about it. All Lannisters pay their debts. We know that's true. Tyrion is a Lannister. We know that's true. Does that guarantee Tyrion pays his debts? Yes. All Lannisters pay their debts. Omar pays his debts. Therefore, Omar is a Lannister. No, that again would be the converse error. And then a little bit later, we're going to get into more complicated ones where they're negation statements. No good deed goes unpunished. You did no good deeds. Therefore, you're going unpunished. Is that true? Or did I just make an error? But now, because it's negations, a forward positive statement is either true or you made the converse error. If I give a statement of negations, it's either true or you made an inverse error. Because remember, inverse is the reverse of the inverse and converse go together. Contrapositive and conditional go together. Now, I know that sounds kind of confusing, but as you start playing around with things, you can show. So now what I want to do, I've been using words. Let's do it symbolically now, and I'm going to show you how you quite simply can prove it. We can prove things, using truth tables, but in a slightly different capacity. Let me find one that I want to do here. My light is not very good in here, so. So let's start with, hold on. Start with the easiest one of all. If P, then Q. P, therefore Q. This is a form of argument. I could also just said P arrow Q. That would have been the same thing. In fact, I'm going to write it like that just so we understand what that means. This happened, followed by this, therefore this. So we're trying to determine, is this a valid or invalid argument? Well, you already know it's valid. If P implies Q and P happens, of course Q happens. But how do I show this? What is the truth table way of doing this problem here? So let's write it down. So I've got P, I've got Q, I've got P implies Q, okay? And let's see, and then I'm going to do it again because it's these three in order that I need to read, but I need these two in order to do this. This is going to seem a little backwards. So let's do this first. So true, 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 false, false, true, false, false. Now, P implies Q. I know that's true. I know that one's false. I know that one's true. I know that one's true. Okay. Now, true, 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 false, false, true, false, false. I need them in the same order. Now I'm actually ignoring this side. What is my premise? These two things together are my premise. Okay, so I'm looking at these two columns. Every part of my premise must be true for me to consider it. So see these guys here? These are not, so these are now irrelevant. These are the only two ways, or these are the only ways my premise was true. Now continue. Look at your conclusion. My premise was true. My conclusion was true. Therefore, this is a valid argument. This is what is called modus ponens. I think it's Latin. Modus ponens is basically you have a really obvious conditional statement. P implies Q, P, therefore Q. Now, there's something else called modus talens that is the contrapositive statement. Okay, P implies Q, P, therefore Q. That's the ultimate ODA. We know that. But here's how we set it up logically. Yes, I repeated myself only because if this had been, let's say, P or Q or something more complicated, I still would have put that there. We look at everything in the premise, and everything in the premise has to be true to consider it. And there will always be a situation where everything in the premise is true. Okay. Now, somebody asked 3 dots. Therefore. Yeah. By the way, that's not even a math term. That's an English term. Yeah, 3 dots always means therefore. So let's do the negation one. I'll start over. So let's say not Q implies not P, not Q, therefore not P. And again, you have a basic feel, you're pretty sure this is true, okay? You're pretty sure this one is true, but I want to show you again, how do I determine if something is a valid argument? It's again, that same truth table and looking at certain positions. Before we were trying to determine if 2 statements were equivalent to each other and we compared their positions on the truth table. We're trying to say, are other things contradictions or tautologies? We were looking at the last thing, is it all truths? Is it all falses? In other words, there's different ways to analyze a truth table. I'm trying to determine now if an argument is a valid argument. So there is a conclusion here. So like before, we start with P and Q. Then I'm going to do, I'll do not P and not Q. I will do not Q implies not P. And then once again, I'm going to do not Q and lastly not P, because I need these 3 things to be the last 3 things so I can compare them. So kind of think of everything that precedes. Let's see. Yeah, everything from here over is almost like scratch work. So keep it simple. True, 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 false, false, true, false, oops, false, false. So not P, false, false, true, true, not Q, false, true, false, true. Not Q implies not P. Be careful. Which one was the lie? Only when this, and it went, because remember I'm going this way with the arrow. So that's the lie. All the other ones would be true then. Okay. Probably should have wrote those in reverse order now that I'm looking at it. Now, not Q, I'll repeat it exactly the same way. Not P. Okay. All I've done is written down truths and falses. I haven't made any conclusions yet. So now let's look. These are my premises. So when are they both true? Only here. And notice my conclusion was also true. That makes this a valid argument. And this, again, like I said, this is modus. Actually, I don't know if I spell it correctly. Talens, Talens, L-L-E-N. I'm thinking Eagles. Modus tollens. The modus just means it's like, your mode of operation. It's one of those kind of terms. One is, think of it as like forward thinking and the other is sort of reverse. This is using contrapositives. the modus ponens is just using conditionals. That's it. That's all that means. Don't worry, I'm never going to ask you as a vocab question, but a lot of you will get used to seeing this in the reading. It's the type of logic that we're using. So let's take something obviously more complicated than this. So let me find one that's a little bit more gnarly. Looking in the homework here. Let's look at sorry, can't see the library. Here we go. So I've got P. P implies Q, not Q and R, therefore R. Oh, wow. So I got three statements here, P, Q, and R. These three things are true at the same time. So you could kind of say they're like being ands, but they're just, I'm making three statements at one time. If I make those three statements and they're all true, can I guarantee this as my conclusion? That's kind of what we're saying here. And you say, well, why is this important? Because these three statements, they could be theorems. They could be mathematical theorems. They could be computer logic, if then else's in a computer situation. As things become more complicated, you'd like to know, what can I assume is absolutely true or not true? Now, this is either valid or it's invalid. Now, why is that important? Again, all squares are rectangles. All rectangles are squares. We say that's invalid. Are some rectangles squares? Yes, that's the problem. A converse statement can be true a lot of the time, but is it always true? That's what we're trying to determine, right? So if I'm thinking, yeah, there are a lot of rectangles that are squares, that's true, but it's not always true. And so that's one of the worst things, is that if something's true sometimes, that doesn't make it true all the time. Remember, for a true statement to be true, it has to always be true. If you find one occurrence where it's not true, then it's simply not true. But that's why you can't prove things true by example. You can only prove things that are false using an example. So how many columns am I going to need? Well, I'm going to need a lot of columns, because I'm going to need a P, a Q, and an R, a not Q, a P implies Q, and a not Q or R. That's a lot of stuff going on there. All right, so I'll write kind of narrow. So I've got P, Q, and R. I'm going to have P implies Q, or actually, sorry, before I do that, I want these, remember, I want the last one. So I'm going to have a not Q. There we go. P, Q, R, not Q. Now in order. Again, the reason I'm going to rewrite the P is so that I can have these as my last four columns, okay? It's much easier to compare. You don't have to rewrite the P, but then when you're looking across a truth table and trying to find the truths, it can just get a little messy because we're going to have 8 rows. So this is just out of convenience. I'm now going to have P implies Q, not Q or R. So obviously I'm going to repeat a couple of them, but I start by putting all of the trues and falses in. Now, this is very deep, so start slowly. True, 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 false. True, false, true, true, false, false. False, true, true, false, true, false. Ooh, false, false, true. Okay, just get it in. False, false, false. Okay, didn't make it by much. Probably started too big. Everything else is now automatic. Remember, this was my choice of what order to put things in. I did it in a logical fashion so I wouldn't get lost or forget something. Once I wrote these down, these are automatic. Okay, there's no choices to be made. I'm just trying to read it correctly. So not Q. So that'd be false, false, true, true, false, false, true, true. I'm restating P for the purposes of reading those last rows. All right, so true, 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 false, 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 false. P implies Q. That's a lie. That's a lie. Those are the only two that are false. All the other ones are true. Remember, if the hypothesis doesn't happen, it can't be a lie. I know it sounds so harsh when you say it like that. It's a lie. Not Q or R. So I'm looking at these two. Remember, or only one of them has to be true. So do I have any double falses? I have a double false here. I have a double false here. And everything else, therefore, is true. So true, 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 true. Hopefully I did. At some point, this starts to look like the Matrix movie, right? All the symbols falling down. And finally, I'm just restating R, all right, which is just alternating true, false, true, false, true, false, true, false, true, false. Now, what am I looking for? I'm very specifically looking for only the situation where the three premises are all true. So where would that be? That would be here. Is that the only place where they're all true? Well, let's see. True, true, false. True, false, true, true, false, false. That's it. Only in the first case were they all true. Now, I'm going to throw a what if at you, okay? And by the way, is our argument valid or invalid? It is valid. Because when the three premises were true, the conclusion did in fact happen, okay? So let me throw a what if at you. Just say hypothetically, what if the next line had been true, true, true? And then the conclusion was false there. That would have made this invalid. But this one said it's valid. If in any conceivable situation, all the premises are true and you have a conclusion that's false. I could have multiple lines, by the way. In fact, in some of the problems, you will do that. You'll have multiple lines where all the premises are true. And in every case where all the premises are true, the conclusion has to be true every single time. So if you have any occurrences where the conclusion is false, then it means it's an invalid argument. And that's why stuff like this is so important, because as the statements get more and more complicated, you know, if I just said, let's make P and Q and R be really simple statements. Let's say P is, let's say Biff is taking discrete math. Q is Biff is taking physics, and R is Biff is really tired of school. Okay. Biff is taking math. If Biff takes math, then he's definitely taking physics. If he's not taking physics or he's exhausted, then he's exhausted. That would be a correct conclusion. I mean, you can have, I like putting things in there, but you can have fun with that. But this is, again, this is essentially computer logic. Let's see. I think we can do one more of these and find another problem. Oh, here's a good one. Okay. Now, you got your work cut out for you. I'm going to give you one and ask you. How about P or R, P implies Q, R implies Q, therefore R. And what I'd like, we're going to take a couple minutes. You're going to do this one on your own. So I will stop recording just briefly. So now that we've finished our table, again, this is the part that's a little bit confusing. This seems to validate your argument. This seems to doubly validate your argument, but that's like finding those rectangles that actually are squares. But here's one where I found the rectangle that was not a square. Therefore, it actually is invalid. By the way, the reason I was not telling you if you're right or wrong, I just wanted to see if you made a conclusion, and most of you did a great job, but did you see that all three of these? That's why this one is just so nasty. It's just so much information here. Now, as long as you're not making any errors writing your T's and F's, you're just reading the answer. You're not calculating anything, and that's actually not too bad. Where this would be really horrible, and you're not going to have this, I'm never going to ask you this question, but where it would be really horrible is if I threw in a fourth variable. Why would that be horrible? Anybody want? It's simple. Anybody know why that would be horrible?
You have twice as many rows.
You'd have 16 rows. Yeah, it's not about the columns, it's you'd have 16 rows. Do you suppose there would be a chance that you might miss a row? One of the comments I made to somebody today, and I think they actually fixed it. One of the comments I made when I was looking at the quiz was I said, well, your truth table is great, but you don't have enough rows. They didn't have 8 rows. They had less than 8 rows. And I'm sure the person, and there was a sense of, I hate to say it, but there was a sense of randomness when they were starting it. You know, it wasn't the head, tail. You kind of have to have organization, because if you don't, you're going to get, if this is an exam and you're already under pressure and stress and you're being timed and all that stuff, and you start randomly writing down these, you're going to leave one out. That's just human nature. You're going to leave one out, or worse, you're going to have 9 rows. By the way, that does happen. You repeated a row inadvertently. Okay, that doesn't make you, a bad person. Like those commercials, just makes you, a bad math student. No, it's bad bookkeeping. So this is what I wanted to show you, that if you can do this, this is the most complicated thing we've done. But it's all about, can I make a conclusion? Now, I gave you a lot of vocab today. Please go through, read the book. I believe this book is so well written that anybody can learn a lot of it. I like what Cynthia said. It's like you're trying to learn football by reading the rules. You can understand the rules, but until you play the game, well, that's why you practice the homework. That's the playing the game part. And the vocab now becomes absolutely huge. I introduced, if you aren't paying attention, I introduced about, I think, 11 terms today. Conditional, converse, inverse, contrapositive, negation, modus ponens, modus talens, necessary, sufficient, valid, invalid. I believe that's 11. And I need you to know what each of those means in their proper context, because you're going to make conclusions. And you might have everything right, but if you have one word that you aren't sure what it means, the conclusion you make could be an incorrect conclusion. And unfortunately, that just kind of messes everything up as you go, right? Because then you won't be able to do the next thing. For those of you who are programmers, I think of things like if, then, else, flow charts, that kind of algorithm. And I remember, because I used to teach programming, if this, then this, else this. You guys remember doing things like that? Oh, okay. So what you're doing is you're making a flow chart. Okay. But if I have even one of those if, then, else's, if I have it incorrect, I'm sending something on the wrong path, then all conclusions at the end will fail. Okay. You guys, if you've ever done your own taxes, you actually have things like this. If this, else go this way, and you're trying to figure out if you got the child tax credit or something. You're doing it. You're trying to figure out, is that a valid deduction? And the nice thing about flow charts is I only have 2 choices generally, this or this. And then I just follow it correctly. But if I make even one mistake, I'm going to end up at the wrong place. And that's the problem. Okay. When you're doing a tree diagram in statistics or probability, we'll do things later on. If I go down the wrong route, I will make the wrong conclusion. Yet everything's binary for the most part. It's this or this. So as long as you're bookkeeping, and I say it laughingly, but distinguishing your T's from your F's is really helpful. There are a lot of the errors that I see, especially on exams, or when people are sloppy and you have that ambiguous symbol that I'm not sure if that's a T or an F. And we say it laughingly. I will actually have a significant percentage of students in this course never use T or F. They will write the words true and false. But don't do that. No, I had students last semester far more clever. They used ones and zeros. It's like, oh, they used 1 for true and 0 for false. Please make sure you're defining which one's which. I would rather you use ones and zeros. Do you really want me to write the word true? I would need a much bigger board. Yeah, I say that kind of laughingly because if you can't read it, I can't read it either. So you want to make sure that this part is absolutely trivial. That's not complicated, but it's bookkeeping, but it's good bookkeeping. All right, we're going to stop there. And like always,